Have you ever felt your phone or laptop get incredibly hot when you're running a heavy game or app? Traditional computers generate a ton of heat, but the next generation of computing, quantum computing, operates on a completely different rulebook. To run the hottest new tech, we actually need to create the coldest place in the universe. But why? Meet the ultimate enemy of the quantum world, thermal noise. Quantum computers use qubits to process information, but these qubits are incredibly fragile. Think of a qubit like a wobbly coin perfectly balancing on its edge. If it gets even a tiny bit warm, the atomic jittering acts like a mini earthquake, knocking the coin over and destroying the data. To stop this, we have to freeze them. And I don't mean winter weather. Room temperature is around 300 Kelvin. To keep qubits stable, we have to chill these chips down to about 0.01 Kelvin. That is a fraction of a degree above absolute zero. It is literally colder than the vacuum of deep space. To achieve this mind-bending temperature, scientists use something that looks like an elaborate piece of steampunk art. It's called a dilution refrigerator, but engineers affectionately call it the quantum chandelier. It's a beautiful, multi-layered cooling system where each level gets progressively colder. At the very bottom of this chandelier, the real magic happens. We use a mixture of two incredibly rare isotopes, helium-3 and helium-4. When these two liquids mix together, they actually absorb ambient heat from their surroundings, pulling the temperature down to that crucial 0.01 Kelvin mark. But the chandelier has a dark side. As we try to build bigger and better quantum computers, we run into the wiring crisis. Every single qubit on the chip needs its own wire to control it. You end up with a massive, tangled waterfall of metallic cables trying to reach a tiny, freezing chip. It's bulky, and worse, those wires leak heat down to the qubits. And the problems don't stop there. That magical helium-3 we rely on, it's incredibly rare on Earth. We are facing a severe helium-3 shortage, making these giant refrigerators ridiculously expensive and unsustainable to run in the future. So, we need new solutions. Enter paradigm shift number 1, hot qubits. Scientists are engineering new types of qubits that can operate at a balmy 1 Kelvin. Now, 1 Kelvin is still freezing to us, but for a quantum engineer, it's like a tropical vacation. It's 100 times warmer than 0.01 Kelvin, which makes cooling drastically easier. Shift 2 is magnetic cooling. Instead of relying on rare liquid helium, we can use solid magnetic materials. By turning on a magnetic field, we force the atoms inside to align perfectly. When we turn the field off, they scramble, and in the process, they naturally absorb heat. It's solid-state cooling. Shift 3 brings the fridge directly to the computer chip. On-chip electronic cooling uses special nanoscale components to actually pump heat-carrying electrons away from the quantum processor. The cooling system is built right into the silicon itself. Shift 4 is the Brownian refrigerator. This sounds wild, but it uses the chaotic, random motion of microscopic particles to actively siphon heat in one direction, pushing it far away from our precious qubits. And finally, Shift 5 is photonic cooling. Yes, we're using lasers to cool things down. Usually, lasers burn things, but by firing highly precise light at a material, we can actually force its atoms to lose energy, lowering their overall temperature without any bulky liquid coolants. The future of the deep freeze is completely transforming. By combining these methods, we are moving away from massive, helium-guzzling chandeliers. The future means higher operating temperatures, solid-state designs, and active, laser precision control. Why does all this matter? Because solving the cooling problem is the absolute key to unlocking quantum advantage. Once we can keep these systems cold at scale, we can move quantum computers out of isolated physics labs and into massive, practical server farms to solve the world's most complex problems, from discovering new medicines to fighting climate change. The next time your laptop overheats, just remember the immense engineering it takes to keep the quantum world quiet. Thanks for watching. Stay curious and stay cool. Don't forget to like and subscribe for more deep dives into the future of tech.